This is a problem on conservation of angular momentum. We have a 2 kilogram bicycle wheel with a radius of 0.3 meters, turns at a constant angular speed of 25 radians per second, when a 0.3 kilogram reflector is at a distance of 0.15 meters from the axle. We're asked what is the angular speed of the wheel when the reflector slides to a distance of 0.25 meters from the axle. And so what's going to happen is as the wheel is turning, the axle will slide from one position outward to the next. And if we think about that, it should slow the wheel down because as a figure skater will put his or her hands outward, that is going to increase the radius and therefore slow the person down. This is a conservation problem, so whenever we have a conservation problem, we want to write or draw a picture of what it looks like before and after, and write our givens according to our conditions before and after. So here is the wheel before where the reflector is closer and after where it's further away. So we have two objects, and for each object we'll write the mass and radius. So mass of the wheel and the radius of the wheel. Mass of the wheel was 2 kilograms and its radius was 0.3 meters. For the reflector as well, we have the mass and radius of the reflector. Mass of the reflector, it said, was 0.3 kilograms, and the initial radius was 0.15 meters. We're going to do the same thing for the final conditions. So 2 kilograms, the radius of the wheel does not change, still 0.3 meters. Mass of the reflector does not change, still 0.3 kilograms. However, the radius of the reflector is now 0.25 meters. Now, for each object, we are going to calculate its moments of inertia. Both before and after we will do those calculations. So we have to look up the equations for the moment of inertia of a hoop, which the tire is a hoop, so that is mr squared. And for a point mass, it is a single dot going in a circle, revolving around a central point. So that is also mr squared. And so we make those calculations. If we separate our givens, it makes the calculation easy. 2 times 0.3 squared, we get a moment of inertia of 0.18, and the units are mass, kilograms, times radius, which is meters, and that is squared. We do the same thing here, 0.3 times 0.15 squared, and we get 0.007 kilograms times meter squared. Then we are going to calculate for the wheel and the reflector afterwards. So the wheel does not change, both the mass and the radius don't change. However, the reflector does change. 0.3 times 0.25 squared gets us 0.01875 kilograms times meter squared. Now we also have the initial and the final velocity. So the initial velocity was told to us was 25 radians per second, and we want to find the final angular velocity. So it's a conservation of momentum problem. And we know that, and I'll write this to the side, momentum, L, is moment of inertia times angular velocity. So we have moment of inertia times initial angular velocity in the beginning is equal to moment of inertia times the final angular velocity again. Now this moment of inertia, because the objects are connected, is simply the total of these two values that we calculated. So we needed the moment of inertia because in this problem, we need the total moment of inertia. So this is the total. Now I'm going to write it out here. I'm going to write it out as the wheel plus the reflector. And I'll do the same thing here. I'll actually write it out. Wheel plus the reflector. So our calculation is 0.18 plus 0.007 times 25 is equal to 0.18 plus 0.01875 times omega f. And we solve for omega f, and we get 23.5, and the units would be radians per second. And it's less than the initial, and that's what we expected. Again, as the reflector slides outward, it's like a figure skater moving his or her hands outward. If you increase the radius, it increases, and we see that it increases the moment of inertia, and therefore will decrease by default the angular velocity. If one goes up, the other must go down if it is to be conserved.